你们如果看那个美国的电视剧哦，常常它最精彩的时候突然就停了，就是说要等到下一个礼拜哦。我不知道台湾的电视剧怎么样，我没有看过还是你看武侠小说都是预知后事如何，请待下回分解，对不对？那我的课也是这样子我们快要知道这个 ring structure， 可是还不知道，所以要等一下，这样子等10分钟好，那我们现在 Okay, now we can determine the ring structure. Okay, so we know that we have this relation. So we know that the equivariant cohomology of S2 is generated as a polynomial ring over R by the two generators U and A. Okay? Because everything can be written as a polynomial in U and A. But you only need A to degree 1. Okay? With one with relation A squared minus U squared is equal to 0. And maybe other relations. Okay? Now what this means is that there's a ring homomorphism from the polynomial ring to the equivariant cohomology ring. Okay? And it's surjective. And since you have this relation, so it is in the kernel of this ring homomorphism, so you can divide out by the ideal and get this ring homomorphism. So we have this ring homomorphism. Okay? Yeah. Now this, well, this is as a module over RU. This says that you don't need A squared because A squared can be written as U squared. So as a module, it's you have only one and A as the generator over RU, right? Because any polynomial in U and A where A occurs to only the first power can be written like this. So this is a free module over R of U of rank 2. Okay, I think this is where I do need that structure theorem for modules over a PID. Okay, this is surjection. I want to know what the kernel is. Okay, so let's call this map. Let's say. Let's call this map alpha, say, and then I want to know what the kernel alpha is. Okay. Now, so R of U is a PID, a principal ideal domain. And then last time I stated a theorem, okay, for module over a PID, which says that a submodule of a free module over a PID is free. Now, and yeah, somebody asked me if it has to be finitely generated. It doesn't have to be finitely generated. Okay, not necessarily finitely generated. Okay, so a submodule of a free module over a PID is free. And let's say the submodule is S and the free module is M. Okay? And so both are free, so they have a rank. The rank is infinity if you don't have finitely many generators. But if M has finite ranks, and so does S. The rank of S is less than or equal to the rank of M. Okay. So this is a theorem from algebra. You could find it in most algebra textbooks like Rotman, or probably in other algebra textbooks too. Okay. So here we have a free module over PID. So therefore, the kernel of alpha is free. And it has a rank, n of rank less than or equal to 2. Okay? Yeah. But this is also free. Free of U module of rank 2. And now when you have free modules, then the middle term is a direct sum of these two. Okay. And so what is the kernel of alpha? It has to be of rank 0, right? Because if it has any rank, and then you take the direct sum with something of rank 2, you'll get rank greater than 2. So it's free. So from the exact sequence, kernel of alpha has rank 0. And free of rank 0, that means it's 0. Okay. Okay. And therefore, alpha from R of UA over A squared minus U squared to the equivariant cohomology of S2 is a ring isomorphism. Okay? Okay. So this gives you the ring structure of equivariant cohomology. Yeah. So in the last problem set, I asked you to work out 3 examples. So you can do all the examples using this method, by first finding the fixed points. And I think they're all isolated fixed points. And then you can try to find the relations this way. Okay? And I think in my book I also work out one other example. Maybe I did P2. Maybe that's in the problem set too. I can't quite remember. Yeah, but now I realize that the proof of the Borel localization formula in the book, it's not quite right? Because there I localize in each degree, and you can't do that. So you just have to localize the ring, all together. All right, so the next result is the localization formula of Atiyah, Bott, Berlin, and Venn. Yeah? And what it says is that if you take an equivariantly closed form and you integrate it over the manifold, you can write that as a sum of over the fixed point set. Okay, so you can convert an integral to a finite sum. And this is obviously very useful for computational purposes because in general it's really hard to calculate integrals on a manifold, but it's fairly easy to do a finite sum. Okay? So in order to state the formula and to prove it, I need a little bit of representation theory. And I don't know how much you know about representations. So basically, you have to know things like what is a representation, what is an irreducible representation, what's a reducible representation, what's a completely reducible representation, what's the direct sum of two representations. And yeah, so I'm just wondering what your background is. So how many people know, what I just said, like those terms? Yeah. And how many people don't? Yeah. Well, so maybe I will spend some time just briefly, discuss representations. And the reason we want to look at representations is that at a fixed point, you always get a representation of the group on the tangent space. Okay? So, lecture 29. Let's see. Local data. Fixed point. So suppose a Lie group G acts on a manifold N, and I always assume that the action is smooth. Then for each G in G, you have a left translation because we're assuming that the action is on the left. And so this is a diffeomorphism. Because it has an inverse, right? You can left translate by G inverse. So there is an isomorphism when you take the differential, okay, and it's going to take the tangent space at x to the tangent space at g times x. Okay. Now, if x is a fixed point, of the action, then the differential will go from the tangent space at x to itself. And so it is represented by a non-singular matrix. So this gives a map from G to GL of the tangent space. So GL of the tangent space, it's the automorphisms. Non-singular automorphisms. Non-singular linear automorphisms from the tangent space to itself. Okay. And moreover, this map, okay, so this map is, this map sends G to the differential of LG. And moreover, it is a group homomorphism because so rho of GH is L of GH star. L of GH means you multiply on the left by GH. So that means you first multiply by H, right? And then you multiply by G. LG composed with LH. And then when you take the differential, it's a covariant functor, so you get LG star composed with LH star, and that's rho G composed with rho H. Okay? So rho is a homomorphism. This. Is a group homomorphism. Okay? Now a group homomorphism from G into GL of a vector space is a representation. A representation of G is a group homomorphism from G into GL V for some vector space V. So at each fixed point, you have a representation of the group in the tangent space. And so therefore, invariance of the representation will give you data at the fixed points. Okay? So that's why we need to know a little bit of representation theory. Yeah, so first let me define the direct sum of two representations. So if rho 1 and rho 2 are two representations, then rho 1 direct sum rho 2 is a new representation. So it's defined by rho 1 plus rho 2 of G. It's okay, it's gonna act on V1, V2. Okay, so it is the vector rho 1G V1, rho 2G V2. Okay? That's a direct sum of two representations. And you can write this as a matrix, rho 1G, 0, 0, rho 2G times V1, V2. Okay? So you have the matrix for rho 1 and the matrix for rho 2. Just put them together like this. Then you get the matrix for rho 1 plus rho 2. Okay? And then W is an invariant subspace of V if rho of G of W is contained in W. Okay? So now, given any representation, what are two invariant subspaces that it has? What's a subspace that always goes to itself? Yeah, 0 and V. Okay? So if 0 and V are the only invariant subspaces, then the representation is irreducible. Okay? Otherwise, it's reducible. Okay? So reducible means that you can find an invariant subspace other than 0 and V. Okay? And rho is completely reducible some of you know representation theory. What's a completely reducible representation?
It's a direct sum of everything.
Yeah. So if rho is the direct sum of irreducible representations. Okay? Now, if you take rho 1 plus rho 2, then of course it's not irreducible because you have an invariant subspace. V1 is an invariant subspace and V2 is an invariant subspace. Okay? So a direct sum of several representations is never irreducible. How about the converse? Is every reducible representation a direct sum? See, a direct sum is a reducible representation, right? So here's an example. Yeah, so the question is every reducible representation a direct sum? In other words, is every reducible, so is every reducible representation completely reducible? If you have a reducible representation, can you write it as a direct sum of irreducible representations? So how many people say no? Okay, all right, good. So what's an example?
Non-diagonalizable representation?
Yeah. So like rho, if you map R to, say, GLR2 by sending T to this matrix 1T 0, 1. This is a homomorphism. Okay, if you multiply two such matrices, you add T and S. Okay, so this is a representation. This representation it has an invariant subspace. Is reducible because the x-axis is an invariant subspace. Yeah, because rho of t times the x-axis. The x-axis looks like that, right? It's 1t 0, 1. Yeah, and you will get star plus, let's see, this, you get star, right? And then 0, 1 times that gives you 0. Yeah, right. Okay. So, so the x-axis is invariant subspace, so it's reducible because it's got an invariant, but it's not completely reducible, because if it's completely reducible, then it has to be diagonal. But this matrix is not diagonalizable. Okay? Yeah. So, but not completely reducible. Okay? Mm-hmm. Now, the theorem from representation theory that we need is that every finite dimensional representation of a compact Lie group is completely reducible. So here in this example, R is not a compact Lie group. So it has representations that's not completely reducible. Okay? But the groups that we're going to be working with are S1 or a torus, or in general a compact Lie group. So it will be completely reducible. Okay? And then Now, some representations may look different, but they're really the same. So, because you can make a change of basis, and then you can go from one representation to another. So, in that case, we call the two representations equivalent. So, two representations, rho v and rho w, are equivalent. If there's an isomorphism F from V to W such that for all G in G, okay, you have this commutative diagram. So you have a representation of G. So you have rho G that goes from V to V, and then rho VG, and rho WG goes from W to W, but you have an isomorphism F here. Okay, so you have this commutative diagram. And that says that once you identify V with W, then rho VG is the same as rho WG. Okay? So if you could do that, then they are commutative. Then the two representations are equivalent. Okay? So we're only interested in non-equivalent, irreducible representations of a compact V group. Okay, so let's look at S1. So then there's a theorem that tells you what all the irreducible representations are. The non-equivalent irreducible representations of S1 are, okay, so do you know this result? What are the non-equivalent irreducible representations of S1? Mm-hmm.
The rotations.
Well, just give me some representations. So, what's... yeah, every group has this representation. What is the simplest representation? Huh? Pardon?
Trivial.
Yeah, the trivial representation. You map the group to one, to the identity. Now, if it's in dimension 2, then it will be reducible. But if it's in dimension 1, it's irreducible. So the trivial representation, okay, that maps 1 to 1, and that's inside GLR. Okay, GLR, they are the non-singular linear maps from R to R. What are they? And, well, it has to be given by a matrix multiplication. So it's given by multiplication by a 1-by-1 matrix. That's a number. That number can't be 0, right? If it's 0, then it's not non-singular. So this is the non-zero real numbers. Okay, that's GLR. And this map, this is a representation. You map everything to 1. Okay, so and it's irreducible. Mm-hmm. So the trivial representation of dimension 1. Okay, and then you know that you have the rotation in the plane. And that, when you rotate in the plane, the only invariant subspace is the origin and the plane, right? So the rotation, L, okay, that sends S1 to GLR2, where L of, say, e to the IT is the rotation matrix cos t sine t minus sine t cos t. So that's an irreducible two-dimensional representation. Okay. So are there others? Yeah, you can just put an M here. Okay. So that's for each t you rotate through mt. Okay, so that's also an irreducible representation. However, some of these are equivalent to each other, right? So, like, if you rotate counterclockwise, like if m is 1, you have this rotation. But if m is minus 1, then you are rotating this way. Okay? And these are equivalent. Because, well, I mean, what's the linear map F that would show that these are equivalent? Yeah, so you can use this linear map, then it's going to turn this rotation into this rotation. So you know that L is equivalent to L to the minus 1. Okay? And in general, L to the m is equivalent to L to the minus m. Okay? So like if you want non-equivalent representations, then well, you can take just positive m. Okay? If m is 0, you get the identity, which is reducible in dimension 2. So for m positive, m is a positive integer. Okay? So these are the irreducible representations of the circle. And let me say that, yeah, in general, Lm is equivalent to L minus m. Okay? So this means equivalent. Okay? Okay. Now, we can now come back to the fixed point of an action. So if you have a fixed point of a circle action, then you get a representation of the circle on the tangent space. Okay? And that's a finite dimensional representation. So you can decompose it into a direct sum of irreducible representations. Okay? Yeah. So now I want to prove a theorem that says if the fixed point is isolated, then that direct sum does not have any trivial representation in it. Okay. So so at a fixed point, x of a circle action on M, we have a representation and so by that theorem, because S1 is a compact Lie group, so rho can be written as a direct sum of irreducible representations of the circle and when you do that, so you get rho is equal to Lm1 plus Lm2 plus you have a finite number of two-dimensional irreducible representations. And then in general, you will have the one-dimensional representations. That's in general. But then the theorem is that if X is an isolated fixed point of a circle action, then rho does not contain any trivial representation as summons. Okay? So you can't have any of these if it's an isolated fixed point. Okay? Okay, now why is that? Well, it's because the group is compact, right? If you have a compact group, now on any manifold you can always put a Riemannian metric on it. But if the group is compact, right, then you can average over the group and produce an invariant Riemannian metric. I think that was in problem set 1. So since S1 is compact, there exists an S1 invariant Riemannian metric on the manifold M. And so in that case, then the action of the group, it's an isometry. Okay, because an isometry means that if you look at two vectors, two tangent vectors, and you look at their image, it's equal to this for all G. Okay, this is true because the metric is invariant. But then it says that LG is an isometry. Now, when you have an isometry, you see, then yeah. So an isometry fit into. So at a fixed point, x. If you have a Riemannian metric, you have the exponential map from some neighborhood of the tangent space to some neighborhood of M. So we have this exponential map. Okay? And it's a diffeomorphism if these neighborhoods are small. And then if you have an isometry, it will fit into this commutative diagram. So you choose V, a fixed point, choose V to be a small open ball about the origin in the tangent space. Okay? And then, because LG star preserves distance, it's going to map that ball to itself. Okay? Then you have a commutative diagram like this. Okay? At a fixed point, choose V to be this open ball. Then there exists a commutative diagram like this. Okay? And where the exponential map is a diffeomorphism. If the ball is small enough, okay? And then, Now, what this says is that under this diffeomorphism, if something is fixed by G, the corresponding image in V will be fixed by LG star. Okay. So let's see. This says LG of x of V is x of LG lower star V. Okay. So if LG lower star V is V, then for all G, then xv is a fixed point of G, right? Because xv will go to xv. Okay. So fixed points in the tangent space will go to fixed points in U. And then, but it's a diffeomorphism, so every point here is of this form. So if this is a fixed point, then this is equal to this, and that's this. This is a diffeomorphism. So then V will be equal to G star V. Okay. So so under the diffeomorphism, fixed points of in V will map to the fixed point set that's in U. And what are the fixed points in V? What kind of space is that? You see, these are linear maps. LG-LORs are linear maps. So a fixed point is precisely an eigenvector with eigenvalue 1. So it's a linear space. Okay? And that's a fixed point set of LG-LOR star. And then when you take different G's, you're just intersecting different linear spaces. So this is a linear space. Linear subspace of the tangent space, okay? But you're only looking at the points that's in V, okay? And so you see, if you have isolated fixed points, okay, that means this linear subspace has to have dimension 0. Right? Because if it has a positive dimension, it will map to something of positive dimension. Okay? Yeah. So if F intersect U is isolated, consists of isolated points, then then this linear, so this linear subspace is the intersection of all the eigenspaces of LG-LOR star with eigenvalue 1, okay, over all G. So this has to be 0. And if you have a 1 here, that means there's a one-dimensional eigenspace with eigenvalue 1 for all G, right? So, yeah. So therefore, this tangent space representation cannot contain a trivial representation of dimension 1. If it has a trivial representation of dimension 1, that would be an eigenspace with eigenvalue 1. So for all the G's, and so the intersection would not be 0. Okay? Okay, so that proves this. Okay? And what that says is that if you have isolated fixed points, then all the M's are non-zero, and the dimension of the tangent space has to be even, because these are all two-dimensional. And then these numbers are invariants of the action at the fixed points. Okay? And so eventually, so the formula for an integral will be in terms of the fixed points, and so it will be in terms of these numbers. These are called the exponents at the fixed points. So, and